finish off decision trees and use that as a kind of case study for making some more general remarks about function approximation. So just to kind of review from last time, in function approximation, we're trying to learn some unknown target function, let's call it f, from some x to some y. Might be from emails to spam or not. That would be our x and our y. Or we had a simple example where the x's were different days described by attributes like the humidity and the temperature, and we were trying to predict whether our friend would play tennis that day. So many functions you can imagine. And in this setting, we say there's some set of instances that the function can take as input. There's some unknown function, and the learner has some way of representing hypotheses which are themselves functions from x to y, different classifiers of email or different classifiers of days. And the input to the system is simply a set of training examples, x, y pairs. Here's the day described by these features, the humidity is high and so forth. And yes, the person plays tennis. And so that's the input, and then we expect that we want our learning algorithm to output the hypothesis that best approximates this unknown function. And so often what we do, of course, is have it instead fit this data, this sample of inputs and outputs of that unknown function. So in the case of decision tree learning, we can easily instantiate this. For decision trees are defined over inputs that are feature vectors of different features that have discrete values. So we talked about humidity could be low or normal or high and so forth. Y has to be discrete valued too. That is, we can predict yes or no, the person plays tennis, or maybe no or yes, but they don't play very well, and yes, they play very well. It could be more than two values. But for decision trees, we don't usually use them for continuous values for y. Although there are extensions to the decision tree learning algorithm that can handle continuous, but we're not here going to cover those. And then, of course, each hypothesis is just a decision tree. And as we said last time, one nice property of decision trees is that they can represent any discrete valued function over any vector of discrete valued input attributes. And so decision trees are sufficiently expressive to represent any function that we might want to teach it. And so what I want to do is, and then we talked about a decision tree learning algorithm, which grows the tree top down. Remember, it starts by picking, well, what attribute should we test at the root of the decision tree? And it used that entropy-based mutual information statistic to do a statistical test to choose the best attribute to put at the root. And then suppose we choose humidity at the root, then we sort high humidity, low humidity, sort our training examples into those two buckets. And if either bucket happens to have uniformly positive or uniformly negative examples, then we stop growing the tree there and just announce that any future example that sorts there should have that label. But if it's a mixture of positive and negative examples, then we just recursively apply the same strategy to further divide by adding more attribute tests to further divide the examples below that point. And we just grow the tree until, well, we said until it perfectly classifies the examples. That is, each one of the leaf nodes in the tree that we've grown has purely positive or purely negative examples. So that was our simple algorithm. And so you can think of this as an algorithm that's really doing a search through the space of all possible decision trees. And at each step, it's adding one more node to the decision tree. And of course, at each step, there are many choices of which node it could add next. And as we discussed, it's using this entropy-based mutual information measure as a way of choosing which of these elaborations of the tree to create at any given point. Okay. So this will actually turn out to be a kind of useful perspective on many, many of the supervised learning function approximation algorithms that we talk about through the course. In fact, in general, we can think of many of these algorithms as performing a search through a space of possible hypotheses. Each decision tree is a different hypothesis about what the target function really is. And many of these algorithms we can characterize as simply performing a search through the space of possible hypotheses for the best one. So I want to pause for a second and talk about this in a little bit more generality. And I have in my head several pictures that I carry around that help me make sense of the field of machine learning. And through the course, you'll see several of these pictures. Today is the first picture. And here's the picture that I think of when I think about function approximation. Okay, so in function approximation generally, we're interested in learning some function that's going to map from x to y, as we said. So now, in our case, in our particular example of decision trees, x is going to be represented as this vector of different attributes. I could call them humidity and temperature and so forth, but in general, I'll just say they're x1 through xn. And so now here's the picture I carry around. Think of the space of all possible hypotheses. I'll call this H. It's just a set of all the possible hypotheses, right? That's just the set of functions that decision tree functions in our case. So there's a decision, whoops, there's a decision tree. That one maybe looks like this. The labels plus, minus, minus. There's a point in that Venn diagram of possible decision tree hypotheses. Here are some others. I won't draw the trees. There are a lot of them. Okay, we also have, think of the Venn diagram of possible instances that the function applies to, the x. And so here's, for example, one point. This is humidity is high, and temperature is low, and so forth. And again, here are some others. I won't draw them out as vectors. I'll just say they're points. And of course, there's a relationship between these two, right? Every one of these decision tree functions or hypotheses actually will label all of these points, right? We can give it, for any given decision tree we're interested in, like that circled one, we could give it all these points and it will give us an assignment that some of them are positive examples, some are negative. Some of them are play tennis equals yes, some of them are play tennis equals no. And so we can think of every one of these hypotheses as corresponding to some set of examples that they label positive. And some set of examples that they label negative. Okay, so now here's a question I want us to think about. I'm interested just in whether you're tracking me. So let's say, suppose for the sake of argument that I have a set of 20 features. N is 20. Okay, and suppose these are also Boolean features. Each of these x sub i's is Boolean. It can take on only a 0 or a 1 value, just to make the arithmetic simple. Then tell me, how many different instances are there in this space? Right, 2 to the power of 20. Right? It's just the number of Boolean numbers I can write down if I have 20 bits. So it's 2 to the 20. So I could say the size of this x is 2 to the n in general, in our case 2 to the 20, which is pretty big. How many h's are there? Y is also binary, thank you, just to be precise. So y can also only be 0 and 1. Okay, so here's a hint. Remember, we agreed last time that decision trees can represent any Boolean valued function over discrete valued attributes like these are. So my question about how big is h is really the same as how many functions are there that you can define over 2 to the 20 instances.
Well, we can count like the maximum number of possible h's, but how much exactly? Because I guess all the trees should be complete. And we, not knowing at least approximate relationships, we can't say how much of complete trees are there.
Ah, that's good. Okay, so the point of this comment, if you didn't hear in the back, was I think that the gist of your comment was that are you asking the number of distinct trees or the number of distinct functions? And let me just ask the number of distinct functions. So the astute observer will notice from that comment that it implies, oh, there are multiple trees that actually represent exactly the same function, and that's true. So how many ways can I label this many examples with positive and negative labels? How many teachable functions are there? That would be a good question. Number of teachable functions. Somebody must know this. Yeah. Right, 2 to the 2 to the 20, right? Because just same argument we used here. We said, well, how many instances can we represent if we have those 20 x sub 1 through x sub 20, and they can all be 1 or 0. And of course, it's just 2 to the n, 2 to the 20. And if I ask, okay, how many ways can I label if I enumerate all 2 to the 20 examples, how many ways can I label them positive and negative? It's 2 to the x, 2 to the magnitude of x. So the number of teachable functions is actually 2 to however many instances I have, which in our case is 2 to the 2 to the 20, which is also a very big number. Okay, now how many of these functions can decision trees represent? That we talked about before. The number of functions decision trees can represent out of these is all of them. Okay, so there are this many different ways that we could try to teach our program by labeling examples. Each one of those different labelings would be a different function that we're trying to teach it. And there are 2 to the 2 to the 20 ways of doing that. But also, as we agreed before, decision trees can represent any one of those functions. Remember, one way would be to grow a decision tree where every path from the root to a leaf is of length 20 and indicates the value for each one of the x sub i's x sub 1, x sub 2, x sub 3, down to x20. And then the only example that could ever sort to that particular leaf is just one example that has exactly that sequence of values. And so we can put a label there that'll be assigned only to that one instance x. So we can effectively grow a big enough tree where every example gets its own leaf node. And then we can label it any way we like. So for that reason, decision trees can represent all of these functions. Okay, so now back to supervised learning. In supervised learning, what happens? Well, the trainer says, here's a positive example. The trainer says, here's a negative. The trainer says, how do I get out of this? The trainer says, here's a negative example. The trainer says, here's another positive example. Oops, that means this decision tree is not really correct, right? And so in this terms of this big picture, each decision tree, of course, has its own set of examples that it labels positive. Here's a decision tree that we like if these are the 3 labeled examples. Here's one that we didn't like as much because it only gets some of the examples labeled correctly. But now let me ask you, well, let me point out that there will in general be multiple decision trees that label the training examples correctly, like this one and this one, but that, of course, don't agree with each other on the label for all the unseen examples, right? And the whole idea of inductive inference is to somehow guess the right function from the labeled examples that we have at hand. And so the issue that I want us to focus on is, what is the basis for generalizing from some finite subset? Some subset of the possible examples have been labeled for us, but not all of them. That's usually the situation we're in. Right? Somebody labels some of the days as ones where we play tennis or not, or somebody labels some emails, but not every possible email, obviously. And somehow we're expected, when we do inductive inference, to go beyond those examples. And part of the point of this big picture is to point out that there's ambiguity here. We're uncertain whether this hypothesis, which gets the correct labels on the training data, or this hypothesis, which also does, is correct. And of course it matters which one we choose because they don't make the same predictions on future examples that we might be confronted with. Okay, so here's the final question. How many examples would we have to label in order to shrink the set of hypotheses that are consistent with the labels down to just one unique decision tree? All of them, right? Right? Because the decision trees can represent every single function, even if we label all of these except for one, that won't be enough because there will still be how many decision trees that are consistent with 2 to the 20 minus 1 labeled examples?
2 to the power of 20 minus 1.
Right, there will be effectively two functions left that are possible. Both of the decision trees that are in the running will label all of the labeled examples correctly. That's what it means to be in the running. But they will disagree on the one example that hasn't yet been labeled. And furthermore, we can't even ask to take a vote because the vote will be 50-50. We can't even ask to take a vote on the unlabeled example. The vote will be 50-50. One tree will say yes, one will say no. If we leave out 2 examples, there will be 4 decision trees, but it'll still be a 50-50 vote if we ask them to vote on the label for an unlabeled example. And in fact, no matter how many we leave out, it'll still be the case that the vote will turn out 50-50 in terms of the trees that might be right voting. So this is a fundamental, sad but true fact about inductive inference, which is that it goes by several names. One name that it goes by is there is no free lunch. We can't really get a program to guess, oh no, okay, I'm going to train myself. There is no free lunch. We can't really get a program to guess the right function until it has seen all of the examples. At least in the case of decision trees, which have what we said was the nice property that they can at least express any teachable function. If they were somehow more restricted, like if we only allowed decision trees up to depth 3, then of course there'd be some functions that they would not be able to represent, decision trees of depth 3, if that was our set of hypotheses. Then we'd have fewer here, but we'd still have that many teachable ones. But then because we had fewer trees, we might not have to see all the examples in order to narrow it down to one. But there'd also be a risk that our trainer might be trying to teach us one of those functions that can't be represented. So in that sense, there's no free lunch, right? If you really want a fully expressive learner capable of expressing any function that could be taught, then the only way that it can reliably estimate that function is to see all the examples. Okay? So this is actually important. And it's true not of just decision trees, of course. It's true of neural networks. It's true of support vector machines. It's true of Bayesian classifiers. It's true of everything. This is a generic. So what do we do in machine learning to build practically useful algorithms? And so what we do, and this is generally how we get around this problem, is we build in some additional assumptions. What kind of assumption? Well, think of our decision tree learning algorithm. What's the assumption we built in there that ends up being the basis by which the algorithm outputs one decision tree, even though there are many consistent with the data? What's the assumption? The assumption is that we're growing the tree from 0 nodes just until it's just big enough to correctly label all the examples. And then we stop growing the tree and we output that tree. Of course, there are elaborations of that tree that also correctly label the training examples and disagree with the one that we output about the labels of future examples. But that's actually the implicit assumption of decision tree learning, that somehow shorter trees are the ones we're going to go with instead of longer trees. And honestly, my real question, the whole point of this discussion is, why on earth is that a reasonable thing to do? I'm disappointed. I love the field of machine learning. I think it has a lot of brilliant people, but I'm disappointed how many advanced researchers in machine learning don't fully grasp this point and don't fully grasp the question of what it would mean to answer the question, why are decision trees, short decision trees, to be preferred over long decision trees? Okay, so let's move on then to, if I knew the answer to that, I'd tell you. But let's push on it a little bit more. So why is it that we decide that even though there are many trees consistent with just that set of 14 examples that we trained the decision tree on last time, in last lecture, that we're going to output the tree that we get to first in this small to larger tree search. Why is that reasonable? So the earliest person we know who talked about this is William of Ockham, who in the 1300s suggested that all other things being equal, we should prefer the simplest hypothesis. And ever since then, philosophers and others have been debating whether and why and when that might be true. Yes?
Why don't we just look for the smallest decision tree instead of using this entropy heuristic?
Why don't we look for the smallest tree? We can do that. Do you want to talk about that now or later?
Sure, we can talk about it now. I mean, that was about to have a discussion later about this, but I mean, that's an excellent question, right? So, I mean, if you're able to do so, then it would be awesome, right? Because then we'll get learning guarantees. But that's a very hard problem, computationally very hard problem. In particular, it is NP-hard. So how many of you guys know about NP-hardness or NP-completeness?
Okay.
So, okay, right. So intuitively, it needs to be NP-hard or NP-complete. Actually, NP-complete, technically speaking, is so NP-complete problems are a wide class of problems that have the property that nobody knows an efficient algorithm, an algorithm that is polynomial in the size of the input. And so if for any of those problems, if we're able to come up with a polynomial time algorithm for that specific problem, like for example in our case, find the smallest decision tree that is consistent with the data, so if we magically had an algorithm for this problem, then we suddenly would have algorithms, efficient algorithms for all these problems that are believed to be very hard, and this is really unlikely. Okay, so that's a great question. I mean, that would be great if we were able to do so, but it's very unlikely. And so that's why we had to rely on heuristics. And this ID3 heuristic is actually a bigger heuristic, I think, and it works well in practice.
Yeah.
And I'll give a couple more comments about it later.
Good. So, but that's a great question. So anyway, I'm going to pause on this question because Professor Balkan is going to have a few more things to say about this a little bit later. So let me just finish up what we want to say about decision trees, and then we'll come back to this question. Okay, so the next thing I want, the final thing really about decision trees, and again, this is not really only about decision trees. This is about function approximation in general in many algorithms, but it's the issue of overfitting. And overfitting intuitively means that we can sometimes get an algorithm that fits the training data very well, but actually doesn't do a very good job on future examples. That can happen for a number of reasons. One can be just statistical coincidences in the small sample of training examples that the algorithm happens to be given. Another way it can happen is if there's noise in the data. That can also exacerbate this tendency toward overfitting. So for example, imagine that here's our tree that we talked about last time that fits those 14 training examples that we presented last time. What if I add a 15th training example, this one here, and this training example is incorrectly labeled by the trainer? There's noise in the labels. So this actually should be a day where play tennis equals yes, but oh, I see. Where play tennis equals yes. And unfortunately, there's an accident in labeling, and so the teacher says no. Well, you can see that our prediction for this was that, well, if the outlook is sunny, we're going to sort this way. And if the humidity is normal, then we're going to sort this way. And so this tree would predict yes instead of no. But if we add this 15th example to our training set, then of course our learner won't output this tree. It'll output some other tree that correctly fits this training example. And so for example, one tree it might output is to replace this by a test on temperature. And since temperature can have 3 values, hot, mild, and low, then the tree will look like this. It'll say, well, in this case, the temperature was hot. That should be labeled a no. Or in these other 2 cases, it'll still be a yes. Okay, so now here's a tree that'll fit all 15 examples, the original 14 plus this 15th one. But you and I know, because I told you that there was noise in the training data, that actually this tree, including the red stuff, won't actually perform as well on future examples as the original tree, which didn't have the misfortune of seeing this noisy data when it was trained. Okay, so noise is one way that we can end up with trees that do very well on the training set. This will perfectly fit all 15 examples. And so if we ask you to estimate from its performance on the training data, what's the error rate of this tree? You'd say 0. It doesn't make any errors. But if we now measure the error rate on future examples, new days that arrive, then the error will be non-zero. So overfitting then is really a matter of the difference between the error rate of some decision tree hypothesis, or in general any hypothesized function, on the training set compared to its true error, that is how well it will really do over the whole universe of examples that it's being presented, the whole distribution of days in the future that it's going to have to label it, play tennis yes or no. And in particular, we'll say, to be precise, that some hypothesis overfits the training data if its measured error on the training data is actually less than its true error, which we would measure if we considered it over if we consider the error rate over the entire distribution of examples, from which the training data is just a little sample. And furthermore, we could say the amount of overfitting is how different those things are. So it turns out this is actually a big deal in machine learning and in decision tree learning. And to show you an example of it, look at this. Here's a plot that shows every place on the horizontal axis represents a different decision tree with a different number of nodes. I generated this plot by actually growing trees from shorter to longer, expanding them breadth first, but using information gain as the way of choosing which node to add next. But I did it to create a breadth first expansion of the tree. And so here we have short tree. It only had 10 nodes. Here's one with 100. And what you see in these two plots is the accuracy on the training data. That's the top plot. Every time I added new nodes to the tree, of course, it became more accurate on the training set. But here you see on the dotted line, the lower curve, its accuracy on a held out subset of the data that originally I had this much data. I held out that much, and I only trained on this much. So the training procedure did not get to see this test data. And here you can see as the tree grew, originally, as we started adding nodes, its accuracy was improving on both sets. But eventually, as we got to the point where even though it was getting better and better on the training set, it was getting worse and worse. And so this is actually the degree of overfitting. Okay. This is the difference between the error rate on the training examples and the error rate on the true distribution. And so you see as Well, this is the overfitting problem. And so in practice, when we train these systems, we have to be aware of this problem and we have to do something about it. Otherwise, if we really let the algorithm grow the tree all the way until it perfectly classifies the training example, we might have a very suboptimal tree in terms of its performance in the future. So what would you do? Your job is, you're now hired as an machine learning algorithm designer. I present this problem to you. You say, don't worry, I took 601. Here's what we'll do. What would you do? How would you modify our algorithm?
Yes? Maybe we can reduce the complexity, the size of tree up to the point that these two line are, up to the intersection, something like that. We can decrease the size of tree.
So we could, you mean we could just say we want to go with this tree, not with that tree. Right. So then, in terms of details, how could we accomplish that? One way we could accomplish that is actually have the program itself do what I did, right? I took the whole set of data that was available, I held out this set, and I only trained on that much. We could write a loop around the decision tree learning program that does the same thing, and at each step after it adds a new node to the tree, it could be plotting the next point in this plot. And it could, in fact, plot this plot. And at the end, when it was all done, it could come back and say, well, gee, I'm not really interested in how well we do on the training data. I'm interested in how well we're going to do in the future. So since this held out test data gives me an unbiased estimate of how well I'll do in the future, I want to go with one of these trees. And that's not uncommon. So people do that. In fact, a slightly more common way of doing this in decision tree learning in particular is what's called reduced error pruning. And the idea is this. You build a tree that classifies the training set correctly, so you do let it go all the way. But then instead of going back to look at how well where the test error optimizes in choosing that tree, you actually do surgery on this created tree, and this gives you a little bit more flexibility. What you do is, once you have the tree grown from the training set, you loop through until further pruning is harmful, and you evaluate for each node in the tree, each internal node in the tree, you say, well, what if I throw away everything below this node and make this a leaf node? And then you greedily do that pruning, making it into a leaf node, for the one choice that most improves the accuracy on this held out validation set. So you have a training set and a validation set. And this means you can actually end up with a tree that was not one of the intermediate steps along the path that you went when you grew the tree. You can actually end up with a different tree that's better. And in fact, this is guaranteed to produce the smallest version of the most accurate subtree. So in that sense, it's better than simply figuring out which of the ones you happen to create along the way performs best. Okay? So this issue of overfitting, we're going to come back to it over and over again. It's at the heart of both machine learning practice and machine learning theory. It turns out we'll actually come up with some theoretical results that tell us how we can bound that expected degree of overfitting in terms of other properties of the learner. And so this is our first exposure to that. Yes?
Sir, in the previous slide, how are we getting the accuracy measure of the tree over the trained data?
Oh, so I'm assuming I'm given initially a set of this many labeled examples. And so when I this many labeled examples. And when I held out this validation set, they're labeled also. And so then I ask, how do I estimate the error rate? What I do is I just look at the fraction of labeled examples that are correctly labeled by the tree. And similarly, I look at the fraction of the held out validation set that's correctly labeled by the tree. Is that the question?
Professor, what I meant was, if you are using 10 examples to train a tree, for all of those 10 examples, always it will accurately predict the value.
So an example comes with a label, right? So let's take an example. Here's a day, and the label is play tennis equals yes. So those labels may or may not be correctly labeled, but they're the best we have. And so even though, of course, what we all would want is to output the function that's going to do the best on the future examples, we don't really know what that function is. The only information we can go by is the training data. And so what we do is, when I say the error over the training set, I talk about the fraction of labels that are in that training set that are matched by the prediction of the decision tree. Some of those might be noisy, and so in fact, but that's the only information we have, and we don't know which ones are noisy if they are. And so as long as we assume they're kind of, reasonable examples, then in practice that's kind of the best we can do. We don't have any other information to go on. Okay, so then let me turn this over to Professor Balkin.
All right. So can you guys hear me? Yes? Okay, cool. So I guess Tom and I thought it would also be a great idea to talk a little bit about provable guarantees for decision tree learning. That means what can we hope to formally show about learning abilities. Okay, and I thought I'll take the chance to actually talk a little bit more generally about the problem of provable guarantees for supervised learning or function approximation, which is what Tom has been talking about so far. Okay, and we've already seen it today, and it was, okay, I used tech point, that's why I have some funny symbols. Okay, cool. So we've already seen it today, but let me say it again explicitly. So in such scenarios, we typically imagine that there is an underlying source of data, an underlying distribution over the space of unlabeled examples, for example, over the space of email messages. And then we assume that in the training phase, first, a random sample of these examples are labeled by an expert. For the spam problem, for instance, we get labels as spam or not spam. Okay? And then this set of labeled examples is given as an input to a learning algorithm, which then produces a hypothesis function, for example, a decision tree, that is then used to classify new subsequent examples that would come from the same underlying source. Okay? So in order to formally talk about this, most often, in most of the existing literature, in order to formally talk about this, we imagine that there is a distribution over the space of unlabeled examples. And we also assume that in the training phase, the algorithm gets to see a random sample of examples coming from the distribution. So you get to see a sample that is identically independently distributed coming from the underlying distribution. Okay, so you get to see an ID sample, small, polynomial in size. And we don't want to see all the examples in the world, because otherwise we'll just be rote learning. So I want to see a small polynomial size sample. Okay, and we see for each example in the sample, we also get to see the label of the example. And then obviously what the learning algorithm can do, it can only use these samples. Okay? But the goal of the learning algorithm, as Tom mentioned, is to come up with a hypothesis function that will have good generalization error, that will do well on new examples that come from the same underlying source. So mathematically, this is a generalization error. The probability that our hypothesis predicts differently from the target function on an example that comes from the same underlying source. Okay, so this is the formalization for supervised learning. And given this formalization, the two key questions that we typically care about in supervised learning are the following. So the first one, and this goes back to a question that you had earlier, so the first question is the algorithm design question or computational complexity question, which asks how can we automatically, in polynomial time, generate hypotheses that do well over the training set. Okay, so that's a computational complexity question. Can we have fast algorithms that do well over the observed data, explain well the observed data? So this is question number one. Now, question number two, and it's equally important, and Tom talked about it already, is the confidence bound or generalization guarantees or sample complexity question, which asks how many training samples do we need to see in order to be confident that if we find the rule that does well over the training set, we'll also do well in the future. Okay, this is exactly what Tom just talked about. Okay, cool. So these are two key questions in supervised machine learning and in machine learning more generally. And one way to think about it, a rephrasing of what I just said, is that the two core resources that we care about when we think about supervised learning are, number one, computation. So that's a computer science question. And the second key resource that we care about is data, the amount of data that we are using. In this supervised learning case, this is the amount of labeled data, which is kind of equivalent to the amount of human labeling effort. Okay, so these are two key resources to keep in mind and the two key questions to think about when you try to think about the guarantees of your algorithms. Now, I want to mention that for the second question, as Tom already mentioned, so there is a beautiful machinery, so very deep math and very deep insights, quantifying in very general scenarios how much data do we need to see in order to be confident that if we find something that does well over the data, we'll also do well in the future. And one such bound is the one that Tom mentioned, the Occam's razor bound. There are other bounds as well, and we'll talk about those later in the course. Now, what is important, okay, so I just want to go back to decision tree learning. So what is important from the decision tree learning point of view is the following, is that what these bounds imply, and again, this goes back to your question, so what these bounds imply, or these generalization bounds imply, is that for the decision tree problem, so at a high level speaking, so if somehow the target function, the function that we're really trying to learn, is a small decision tree, so its description is only polynomially in the number of input attributes. So if the target function is a small decision tree, and if we somehow are able to find a small decision tree that explains the data well in polynomial time, then we immediately would get good generalization guarantees. Yeah? So if we're able to solve the problem of, here is a set of labeled examples, please find for me the smallest decision tree that explains this set of labeled examples, and moreover, I promise you that there exists one. Okay, so if I'm able to solve this problem, then I would be done, because there is this beautiful machinery that says we're going to have learnability guarantees. Okay, so everything would be easy. But unfortunately, it turns out that this question of finding the smallest decision tree that is consistent with a set of labeled examples, it's probably very hard. Formally speaking, is NP hard. Okay, and this was proven actually by Ron Rivest in '76, so many years ago. Okay, and as I mentioned already, what NP hard means, because there are people here that don't have a necessary computer science background, so what NP hard means is just means something that is believed to be really hard. You don't expect to find the polynomial time algorithm in the near future, because if we're able to do so, we'd have polynomial time algorithms for many more problems, and that's strongly believed to not be possible. Okay, cool. So, we cannot solve the immediate optimization problem that we care about, but of course, what we can do next is to think about smart heuristics, and this is what people have done. And Tom already mentioned one of them. This is ID3. So this is a top-down approach for decision tree learning, for finding a decision tree that does well over the data. And as Tom mentioned, this is a greedy approach where we grow the tree from the roots to the leaves by repeatedly replacing an existing leaf with an internal node. And so this is a very natural approach. Obviously, the only thing that is left to specify is the splitting criterion. And as we've seen in ID3, the splitting criterion is to pick the leaf that decreases the entropy the most, okay, that has the highest information gain. Okay, so that's very natural. And Tom showed us pictures that does very well on real data. Okay, but you might wonder, you in particular, because you also asked a different question earlier, so you might wonder, why is the information gain? Why not a different splitting criterion? What's so special about it? Okay, and in particular, an even more basic question I would expect at this point is why, because at the end of the day, what we really care about is basically getting a tree that has the smallest error rate over the given sample. So why not choose to split a leaf so that after I do the split, I decrease the error rate? Because this is my true goal, right? To decrease the error rate. So why not to choose to split a leaf so that the error rate decreases? Why not do locally what we want to achieve globally? Okay? And I guess the answer to this question is interesting. It turns out that you can get stuck in local minima. And if you try to do so, and I'm not going to go through details, you're going to have an example of this type in your homework. But you can construct very simple examples where the target function, some symbols are missing. Yeah, you can construct very simple examples where the target function is very simple, for example, a conjunction, and where basically if you are trying to choose, even if you are at the root, if you are trying to do a split that decreases the error rate, it's just impossible. So there is no way to make progress according to the error rate locally. Okay? But it turns out that for such examples, and again, you're going to see this in your homework as an example. Now, it turns out that for such examples, like this one that I just mentioned, the entropy always decreases. So somehow some symbols disappeared from the slides, I guess because of the translation, but it's okay, it's irrelevant. Okay, so there are examples where if we are trying to reduce the error rate, we cannot make any progress, we are stuck in local minima. However, in these examples, the entropy always decreases. And it turns out that even more interestingly, you can show that kind of for a broad class of problems, trying to use the entropy as a local measure of progress is a good idea. And in particular, we can, so there is a beautiful result by Kearns and Mansour that shows that if the measure of progress is entropy, then we can always guarantee success of our algorithm under some formal relationships between the class of splits and the target function. And I mean, this is a little bit too advanced at this point. I'm just going to mention the words. What we really mean here, we want the class of splits. We want the class of splits to kind of be to provide a weak approximation for the target function. We want them to be weak learners. Okay, I know this is a bit advanced. Please ignore the details. The important point here is that there is a very general family of problems for which entropy turns out to be a good measure of progress locally. And what's nice is this provides a very nice way to think about the effectiveness of various top-down algorithms, and it shows that this ID3 heuristic has very strong formal guarantees. And again, I'm not going to go through details, so please come to my office hours if you're curious. But just one sentence I want to say is that actually this, so the key insight in this formal work is actually very easy to even describe, and it all boils down to the fact that the entropy is a strong concave function as opposed to error rate is kind of a linear function. And this turns out to be crucial in order to be able to guarantee that we'll always be able to find a good leaf to split if the weak learning assumption is satisfied. Okay? Again, this is a bit advanced, but please come and talk to me if you're curious. Right, and so I guess I'm not going to go through this because it's a bit too much right now, but I guess to sum up, so the key questions, I think this is the most important part of this discussion is, so the two key questions that we care about in machine learning, when we do supervised machine learning, are the algorithm design question, how can we generate rules that dwell over the training data, and we want to do this fast, in polynomial time, as efficiently as possible. Okay, and the second key question is confidence bounds or generalization guarantees. Okay. I guess we've also seen that for the first question, sometimes solving the most natural optimization problem, like find the smallest decision tree consistent with the data, that could be hard. So in those cases, what we might want to think about is smart heuristics and try to analyze them under natural conditions about the data, and still have good insights when to apply one versus another. Great. So questions? Yeah?
So for the entropy thing, does any concave function work?
Any concave function would work. Yeah. So entropy actually is not the best function. So if I go back here, entropy is not the best function. What we really want is the more strongly concave the function is, the better it is for us. And actually, this paper that I mentioned proposes an even better function. Cool. All right. Great. Oh, more questions? Yeah.
Error rate function always be a linear function?
It's not linear. It was linear in my, yeah, it's actually not really linear. I meant linear in this very specific example. So when I have just two labels, and I really meant linear in a specific sense on the fraction of positives is more than a half and so on. It's, don't take it too precisely. I mean, in particular, what I mean here by linear, I mean is really the error rate is like if you're at a node, my node V over there, and the fraction of positives is Q, then the error rate is really the minimum of Q and 1 minus Q. And when you plot it down, is this like green function, which is linear up to a half and decreases again. I mean, this is what I meant. I went very quickly through it. Yeah.
What if it happens that in all possible choices of leads, we will get in a situation when the entropy will be almost equal all of them? How we'll choose? How the algorithm will choose which one to, which attribute do you check next?
I guess that's a good question. So I guess mathematically you could choose any of them that decreases the entropy if one exists. And as I mentioned, under certain general properties about the data, this will always be true. I guess, Tom, do you have other comments?
I agree.
You agree? Okay, cool. So all we really want is to just decrease the entropy, I mean, to make progress.
Yeah,
and if our,
yeah,
okay, there could be secondary criteria. Okay, so okay, I mean, for your application, there might be other secondary criteria. You might want to take those into account. Great, more questions? All right, if there are no more questions, I guess Tom will talk about material that is relevant, I guess, to the second point, probability theory, which is crucial for generalization bounds.
Right. I need my mic back.
Okay, great.
Great. Thank you. So you'll find in the literature, by the way, that for any of these algorithms that are widely used, like decision trees, that there's a lot of work that's gone into both practical tweaks on the algorithms to make them work on larger, better on various kinds of data, and also quite a bit of theoretical work if they're popular algorithms, like the kind of thing that we just heard from Professor Balkan. So here's what I think is the minimum stuff you should know from what we've covered so far then. First, the idea of a well-posed function approximation problem. Okay. Some instances, some function to be learned. We have a sample of inputs and outputs of that function. Second, the idea that learning is really, one thing you can think of it as is very closely related to search problems, searching through the hypothesis space. Or if you prefer, think of it as an optimization problem. We're trying to find the optimal hypothesis in this hypothesis space for some definition of optimal, right? For us, for decision tree learning, it's kind of funny because the algorithm itself doesn't actually have a property that we can prove is being optimized when it outputs the tree, but it's closely related to the shortest tree that correctly labels the examples. And there are, in fact, lots of different objective functions we'll be talking about that get optimized. The idea that you can't really there is no free lunch. You can't really do inductive learning without some kind of additional assumption beyond just the information in those training examples. In the case of decision trees, we rely heavily on the assumption that smaller trees are to be preferred over big trees. And then decision tree learning algorithm itself. Now in the slides you'll notice I put a number of additional slides that I'm not going to cover, but that kind of suggest extensions to decision tree algorithm. For example, what if the attributes are not discrete valued but continuous? We can do things like put thresholds on those. There are ways of doing that. There are other pruning methods. There are ways of dealing. What if some of the x sub i's, some of those attributes are unobserved for some of the examples? Can we still use decision tree learning? Yes, we can. There are ways of extending it to handle that. And I put a number of questions that I think would be fun for you to think about, and maybe bring up some of those in the recitation section. But take a look at those at your leisure. So there's much more that we could say about decision tree learning, but that's not what this course is about. This course is about machine learning, so we need to move on. Okay, so speaking of moving on, you'll notice that we have carefully avoided so far any discussion really about probabilities in the learning algorithm. But it turns out that much of the most successful parts of machine learning really are founded on probabilistic reasoning. So I want to use the rest of today just to do a lickety-split, very fast, quick survey, reminder, remedial refresher on probabilities. So here we go. There are a number of things that you have already been exposed to if you've had a course in probability and statistics. But all of them really start with the idea of random variables. So random variable, the simple way to think about it, it's a variable that denotes something about which we're uncertain. I always think of a random variable as something whose value is an outcome of a random experiment. So for example, the random variable A I could define as it's true or false. And in fact, it's going to be true if a randomly drawn person from this class is female. False. Okay? I could do that experiment again, and I get a different value for that random variable. And associated with that probability, with that random variable, is actually a probability distribution. There's some probability that if I do it, I'll get true, female, and there's some probability that I'll get false. You could probably estimate that probability if you look around the room. But a random variable is nothing more than an indicator, a variable whose value is the result of a random experiment. So many kinds of those. We define the probability, if it's a random variable with just true and false, then we'll define the probability that A is true is just the fraction of possible worlds in which it's true. And we could think of, more precisely, there's a sample space, the set of, for example, the sample space for this random variable could be the set of all the students in the class. And each time I take a draw of the random variable, I'm doing this random experiment, getting a true or a false. And if you had to estimate the probability that I'll get a true, you would just look at the fraction of females in the class, and that would give you a good estimate of the probability of it being true. Okay, so more formally, we say that we have a sample space S, for example, the students in the class. We have a random variable is really just a function defined over that sample space. If I point at any one of you, I get a true or a false, female or not. And an event could be a more complex thing. It could be, if I had, say, two random variables, one is A, female or male, and another random variable is B, blue eyes or not, then I can also define complex events like A and not B, a female without blue eyes. And so more generally, we have events which are also subsets of the sample space. Okay, so there are a lot of rules of probability that you may be familiar with already. You'll be more familiar as the course goes, as we go through the course. One way to think about random variables is in terms of Venn diagram of the sample space, and I could say this reddish area is the set of worlds or the part of the sample space for which A is true, and that's embedded in this larger Venn diagram of all possible outcomes of my experiment. Probability is based one way to think about probabilities, it's based on a set of axioms. Here they are. They're very simple. Say things like the probability of any random variable A needs to be between 0 and 1. If the value is true, then the probability of the value true is 1 and a false is 0. And the probability of a disjunction of two variables is the sum of their individual probabilities minus their conjunction. It turns out if you start with these axioms, then you can prove, well, you don't have to because the Finetti already did, that you really should take these axioms seriously, in the sense that if you gamble based on an uncertainty calculus that does not obey these axioms, then you can be exploited by me because I obey these axioms. So you never want to gamble against using a probabilistic system that opposes these axioms, because your probabilistic system can be provably inferior to this. Many of the intuitions behind probability formulas follow from these kind of Venn diagrams. So again, if we think of a random variable like A, here's the sample space of possible worlds. A could be true or false. I think if this is the probability, this area gives the probability that A is true, this area that it's false. And then from here we can well, let me just say, here's one of the rules of probability that can be proven from those axioms. The proof is actually easy. You could do it yourself as an exercise. I give it here. It's just based on the idea that if A and B are Boolean variables, then we just use the rules of Boolean logic to start out by saying A must be equal. If A is true or false, a Boolean variable, then it's just equal to A and B or not B. And then there's some arithmetic that allows us to re-express this and prove it. But the essence of this is that if we happen to know the probability of the joint A and B assignments, we can use that to calculate the margin, just the probability of A alone. That's valuable. Here we can see the same rule, but in pictures. If I want to know the probability of A, that's actually the area of this green region. Well, that's just the probability that A is true and B is true, which is this region, plus the probability that A is true but not B, which is that region. And so here in pictures, it's very easy to see the intuition behind that proof. Conditional probability. And sometimes I'm interested in what's the probability that A is true given that B is true. The answer to that is, here's the definition. We say that it's the probability that A and B are both true divided by the probability of B. For example, what's the probability that you have blue eyes given that you're female? If this is female and this is blue eyes, then that formula says the conditional probability of having blue eyes given that you're female is the ratio of the probability that both things are true, that's this, divided by just the probability that B is true. And so the conditional probability is just the proportion of cases in which B is true for which A is also true, and that's what the formula says. So these are another kind of picture that I carry around in my head whenever I see some expression and I want to just sanity check on it. Often these kind of Venn diagrams go a long way. A corollary of this definition of conditional probability is what we call the chain rule, which says that if we want to know the probability of the conjunction of two things, we can factor it this way. You can see it up there. It's just multiply both sides by P of B. But actually, this chain rule we'll use much in this class, in particular when we talk about Bayesian belief networks. And it's in its more general form, it applies not just to pairs of things, but to any length conjunction. So for example, it's also true that if I want to know the joint probability of three things, then again I can factor it into P of A and B and C times the probability of B and C. But then if I like, I could apply this rule again and say, well, that's just the probability of B given C times the probability of C. So this, in fact, and so you can kind of see why this is called the chain rule. If I have a conjunction of n of these, I can factor it into n terms, each of which peels off one of those variables to put it on the left side. Okay, Bayes' rule. Bayes' rule, again, is at the heart of what we're going to be doing. The simple way to see Bayes' rule is to start with what we just saw on the previous slide. We say, well, we now know we can write P of A and B as just the probability of A given B times the probability of B. That's what we just saw in the chain rule. But of course, that also could be written the other way. I could say P of B given A times the probability of A, right? P of A and B is the same as P of B and A. And if I wrote it that way, I get this. So these two things are equal. That's a curvy equal sign. So this is effectively Bayes' rule, although it's usually written this way. You say, if I want to know P of A given B, then that will be equal to P of B given A times P of A divided by this guy up here, divided by P of B. And this is Bayes' rule. It tells us how we can calculate the conditional probability of A given B from these quantities. Okay. In fact, there's Bayes himself. And there are a few other forms of this. And here's an example to apply it. I'm going to stop there, but I didn't expect that if you've never seen probability before, you would be able to get it from that quick sweep. But I expect that all of you have seen probability before. And as you're doing the homework for this week, you'll see there are some questions about probability that you're asked to answer. And so please do look at do get that homework, take it seriously. Even though you're encouraged to work with each other to solve the questions, the reason we want you to work with each other is so that you can teach each other the different aspects of this stuff that you know. So next time we'll actually pick up on this, and we'll, for our next algorithm we're going to talk about is actually Bayesian classifiers. So take it from there.